Good morning, student. So, welcome to Urban Pro. In this session, I am going to discuss lenses and mirrors. So, first I'll discuss lens. See, in lens, we have very interesting subtopic that is displacement method. What is that actually? Displacement method. This is actually definitely it is in our syllabus as well as it is very useful in the laboratory to find the focal length of lens, to measure the focal length of lens, convex lens. Okay, so see what is the thing is, there is a object. Suppose this is the object. Okay, and we have a screen here. This is screen. Let me write it as object. This is object and this is screen. Okay, the distance between the object and the screen is, we take it as capital D. Now we will place a lens. Suppose we place a lens in between the object and the screen. This is a convex lens of focal length f. Okay, the distance between the object and the lens is u and the distance between the screen and the lens is v, object distance and image distance, as you know. Okay, so as we have taken the d is the distance between the object and the screen, so we can substitute this distance, image distance, by d minus u. Correct? Okay, now you know the equation of lens, that is 1 by v minus 1 by u is equals to 1 by f. V is the object image distance, u is the object distance, f is the focal length. Now we will put the value u, d minus u and f. In place of v, we will write d minus u minus u. U will write as minus u. Why? The object is behind this mirror and light is passing through like this. So this is the positive direction and the object is behind this lens. So it is minus u. Just obeying the sign convention is equals to 1 by f. What it gives? It will give u times d minus u, and in numerator it will be u. See, this minus, they will actually turn out to be plus. So I erase this minus here. Okay, so it will be d minus u, so it will be u only, and here d minus u is equals to 1 by f. So this plus mu and this minus mu will be cancelled out. We will left with d by du minus u square is equals to 1 by f. Let us multiply. So it will be du minus u square is equals to df. So u square minus du plus df is equals to 0. We have a quadratic equation of u. Now we will solve this to find the value of u. Okay, we will solve this to find out the value of u. How to find that? You will, u is equals to minus b, that is here d, plus minus root b square, that is d square, minus 4ac, that is 4 times a, that is the coefficient of u square, that is 1 here, and c for ac, c is d here, by 2 into a means 1. So let us write it precisely. U is equals to plus d means d only, plus minus root under d square minus, sorry, here it will be f, for f it will be f, isn't it, by 2. Fine. So here we see that we are getting two values of u. First one, u1, we write it by u1 is equals to d plus root d square minus 4f by 2, and u2 is equals to, now we will consider the negative sign, d minus d square minus 4f by 2. Okay, so we are getting two values of u1 and u2. But before that, we have to consider whether this term that is within this square root is positive or negative. If this term is negative, then there is imaginary term. The u will become imaginary. So there is no possible position of the lens for which we will get an image on the screen, isn't it? So before that, let us discuss for two cases, two or three cases. Suppose this case one. In case one, we will discuss, suppose d square is less than 4f. When d square is less than 4f, what happens? The u is imaginary. U is imaginary. That is, it means no position. For no position of the lens, no position of lens, let me erase this. This will be useful after some time. Okay, for no position of lens, image will be formed. That is, image will be formed on screen. That is, image will not be formed. Fine. So if d square, that is the distance between the object and the screen, the square of this distance is less than the 4 times the focal length of the lens, then there is no possibility of image formation on the screen. Okay, now we will consider case 2, where we will consider case 2 where we'll assume this d square is equals to 4f. Maybe the d square of the distance between the object and the screen is equals to 4 times the length of the lens. Then what will happen? See, focus on the value of this u. It will become, the u will become, then this will imply u is equals to, as these are equal, then this term d square minus 4f will become 0. So we will have only d by 2. So d by 2 is the position of the lens for which we will get the image. Correct. So let us conclude here something. We will write something about the image formation in this condition. In this condition, what we can write? We can write image will be formed when lens will be at the midpoint of object and screen. Okay, or it is better to write sharp image, that is it will be focused. Sharp image will be formed when the lens will be at the midpoint of the object on the screen. One more point we can write, see, as we see here, u is equals to d by 2 from the diagram. If this distance is d by 2, d is the total distance. If the object distance is d by 2, then the image distance will also be d by 2, isn't it? So let me write, so the image distance, that is in short we can write as u is equals to d by 2, v will be also d by 2. What do we see here from this? Object distance is equals to image distance. Object distance is equals to image distance, isn't it? When we find this scenario, when the object distance becomes image distance, when the object is at a distance 2f, that is twice the focal length, isn't it? When the object is at 2f, the image is also formed at 2f. So object is at 2f distance, correct? Fine. So this is all about, okay, we can also conclude one more thing. What do we see in this case? We see when the object and the image is formed at 2f, the magnification or the size of the object, size of image is equals to size of object, isn't it? Size of the object and the image becomes equal when they are at 2f distance, and this is the case when d square is equals to 4f, that is the square of the distance between the object and the screen is 4 times that of the focal length of the lens. Okay, now one more case we have to discuss. This was case 1 where d square is less than 4f. Then we discussed d square equals to 4f. Now you can easily get what I am going to discuss, that is nothing but d square, so case will be case 3, which will be d square greater than, it is the case which is d square is greater than 4f. When the d square is greater than 4f, then definitely there is a value, definitely it is not imaginary, d square is greater than, so there will be value, isn't it? So this will become nothing but u is equals to what? U will become, as it was, d plus minus root d square minus 4f by 2. So we will have values, the root over d square minus 4f, it will have value, it will not imaginary, it will not 0. So as here we have plus and minus 2 values, so we will have 2 values from this, that is u1 is equals to, will give d, initially will take plus sign, d plus d square minus 4f by 2, and another u2 is d minus d square minus 4f by 2. So what we can conclude here? We can conclude there are two positions. There are two positions of lens for which we get sharp image on screen. Okay, great. See, we have two values, u1 and u2. Let us check what will be the corresponding image distance as we calculated it in case the second case as well, isn't it? See, initially we calculated the object distance and we calculated the corresponding image distance, and it appeared the object distance is equals to the image distance. From that we find that the size is same as object, they are at situated at 2f. Now we will check similarly what will be the positions, what will be this and that when the d square is greater than 4f. Now initially we have the object distance two object distance, isn't it? So we'll now find the image distance corresponding to u1 and u2. Okay, see, it is very simple. See, it is very simple. We want to calculate the image distance when the lens is at u1 distance. Okay, so it is nothing but v1. So v1 is what? Listen, come to the diagram. This one is u1. Then this one will be what? Nothing but d minus u1, as the total distance is d, isn't it? So the image distance is nothing but v1 is equals to, we will write d minus u1. What is u1? We will put this d minus u1. That is, we'll take this one. What is this? It is nothing but d plus root d square minus 4f by 2. Let us calculate it. It will give 2 in the denominator, and in the numerator, see, there will be 2d minus d plus d square minus 4f, isn't it? What it will give? It will give, let me make some space here, although I have space, but it will be better if I write in this fashion. What it will give? 2 will be denominator as it is. See here, 2d minus d will give d only plus root of d square minus 4f, isn't it? Similarly, we will calculate v2, that is the image distance when the object is, the object distance is u1, or the image is at u1. Okay, so this is the same case. Sorry, it is not u1, it is u2. It is u2 as u1. No, it will be u2. So d minus u2. Now we'll put the value of u2 here. That is, you see, we are putting the value of u2, that is d minus root of d square minus 4f by 2. What it will give? It will give, similarly, in denominator it will be 2, and in numerator I am not calculating it again. You calculate it. It will become d minus, I hope, what it will give? It was d plus. Okay, now it will be 2d. It will be 2d minus d, 2d minus d plus root of d square minus 4f. I am getting 1 second. It will be d square, it is minus, so it is 2d minus d, 2d minus d. Okay, here a negative sign will be there. A negative sign will be there. A negative sign will be there. And here it is fine. That is, it will give d plus root of d square minus 4f by 2. Here the interesting thing is, you see, what is this? This is nothing but v1. This is v1, and it is also nothing but u2. The expression for u2 and v1 is same. So we will mention it here that v1, we will mention it here, v1 is equals to nothing but u2. Similarly, the value of v2, that is this one, the value of v2 is same as u1. It is same as u1. You can check. This is v2. That is the object distance when, sorry, the image distance when the lens is at the second position. This distance is equals to the position of the lens, the object distance, when the lens is at the first position, isn't it? So we will write v1 is equals to u2 and v2 is equals to u1. We notice this. Okay, so what conclusion can be drawn from this? We can conclude that the object distance and image distance can be interchangeable. Okay, can be interchangeable. We can conclude this, isn't it? So this was all about this displacement method. Using this, we can measure the focus or focal length of this convex lens in laboratory. Okay, we actually find two positions for which we get a sharp image on the screen. Then we measure the U1, U2, and from that we measure focal length. Okay, now we will move on to discussion of mirror. Definitely we will discuss on spherical mirror, as you are in class 12, now you are not in class 10. So we will discuss about spherical mirror. Okay, spherical mirror. See, definitely you know the formulas, this and that, but I have seen many students, they are sometimes confused with the ray diagrams when we discuss about this reflection using a spherical mirror. Okay, so we'll now discuss the ray diagram of spherical mirror. Okay, so how many spherical mirrors are there? There are only two types of spherical mirrors. One of them is convex mirror, and another is concave mirror. Which one we will discuss first? See, we have only two cases in case of convex mirror, and I guess 4 to 5 cases in concave mirror. So it will be better to start with convex mirror. Okay, so the case is ray diagram of image formation. The topic is ray diagram for image formation by convex mirror. Okay, so it will be better if I write it in small d. Okay, see, we have only two cases. The case one is, suppose this is the, we are talking about convex mirror. So the convex mirror can be drawn like this. This is the silvering. Okay, and suppose this is what? Principal axis. Now, parallel rays are coming from infinity. That is, the object is at infinity. So all the rays which are being incident on the mirror, on the spherical convex mirror, are parallel to the principal axis. Okay. After reflection, what will happen? They will be reflected back in such a direction that will be passing through the focus. Okay, suppose it will be better if I draw the focus first. So suppose this is the focus. Okay, then the image will be the after reflection, the reflected ray will be reflected like this, isn't it? Similarly, we have to draw the ray diagram for this. This will look like this, isn't it? So this is the ray diagram. The image will be formed at focus. Let me write, for object distance is equals to infinity. The image distance will be what? Nothing but the focus distance. This is the distance we measure from pole to focus. This is f, isn't it? This is the image distance. What conclusion we can draw? This is virtual image. This is virtual image as the image is being formed behind the mirror, isn't it? Okay. The second case, that is, we know in case of convex mirror, the image is always virtual. The image is always virtual. What we will do is, it will be better if I just copy and paste it. Then our time will be saved. Okay. So this is the ray diagram when the object is at infinity. So I have to erase some part of this. So let me erase this. Okay. So this is the focus. Okay. So this is, I have no use actually. Okay. Suppose this is the focus. Okay. Now I place an object somewhere here. Okay. Somewhere here. What will be the case? A parallel ray will come parallel to the principal axis. After reflection, it will appear as if it is passing through the focus. The red point is our focus. So it will be reflected back in this direction. Okay, fine. Now, as you know, we need at least two rays to draw the ray diagram. Now we will take another ray which will come from the tip of this object arrow. Suppose this is incident at the pole. This is incident at the pole. After reflection, as you know, here at the pole, the blue line, that is the principal axis, is the perpendicular. So this is the angle of incidence. So the angle of reflection will be what? It will be something like this. Now we will extend it in the backward direction. They meet here. So the image is this one. This is the tip. Okay. So which one is the object? This is the real object. Definitely object is always real. And this is the image, but it is virtual image. Correct? It is virtual image. What conclusion we can draw? We can conclude that the size is less. Size is less. Here the size was, in case of the first case, size is very less, we can say, not very less, we can say less. I mean, less. But in case of the second case, okay, in case it was very less actually, because it was a point like size is very less, and here size is less, we can write only size is less. Definitely it is virtual. It is virtual. And what is the distance? We can't say distance, we have to calculate it in this case using the formula 1 by v plus 1 by u is equals to 1 by f. Okay, and you know f is equals to r by 2 in case of spherical mirrors. Okay, these are the cases for ray diagram of image formation by convex mirror. Now we will move on to the ray diagram of image formation by concave mirror. Okay, so ray diagram of image formation by concave mirror. Okay, so what are the cases here? Initially, it is concave mirror. So this is the case. I have to draw it like this. Here, the silvering will be like this. And what is this? This is the principal axis. Let me keep the principal axis at the middle of this lens. Here, let me erase. Okay, so this is the concave mirror. This is the principal axis. Initially, let the object be at infinity. When the object is at infinity, so u is infinity. Okay, so all the rays that will come will appear parallel to the principal axis because they will be parallel because they are coming from infinity. So after reflection, what will happen? It is very easy, as you know. It will pass through the focus. It will pass through focus after reflection. So after reflection, they will pass through this. And what conclusion we can draw here? The image distance V will be the focal length. As you know, this distance is the focal length, the distance from the focus and the pole is F. And the size of the image is what? Point size, point like image, isn't it? And we can say real image because we are getting the image by the intersection of the reflected rays. It is, we are not getting like in the last cases. In case of convex mirror, we get the image by the intersection of the extension of the reflected rays, not the not the reflected rays, but the extension of reflected rays. But here we get the reflected rays get intersected here, so definitely this is real, isn't it? So the second case we will discuss. uh, Let me copy this. We will paste it here. What we have to erase? Definitely these rays will be different. Here this is focus, but forget about this. Okay, now this is focus. Suppose this is 2f, this is focus. So this is, we can let us, it is 2f, although we do not represent it. Okay, we can write it as in case of mirror, as you know, it is center of curvature, we can write it C. Okay, in the backward also, here also it is F, here also it is C. Okay, C is the center of curvature, you know, this and that. Now I place the object at not infinity but greater than 2f. Okay, so here U is greater than 2f, not infinity. Okay, we can also write U is greater than f but less than greater than 2f, greater than, it is greater than 2f but it is less than infinity. We can write this way as well. Okay, what happens in this case is parallel ray. We need to consider two rays, one parallel to the principal axis. After reflection, it will pass through the focus like this only. This is the ray, and we need one more ray. Let us take it. Suppose I take a ray which passes through the center of curvature. The ray which passes through center of curvature, it actually incident on the mirror perpendicularly. So here the angle of incidence is equals to 0, angle of reflection will be 0. That is why the ray will actually trace back into its initial path, isn't it? So the image will be which one? The image will be this one. This is the tip of this arrow. The image of the tip of the arrow is this one. So here the image will be this one, will be the image. Okay, so let me write, this is object and this is image. Okay, what conclude we can? We can conclude here size is less. It is real. The image is real. Its position is where? It is, the distance is greater than f, less than 2f, isn't it? The center of curvature, the distance between the pole and the center of curvature is 2f. Okay, so I'm not going to draw all the ray diagrams. Following these rules, you can draw rest of the cases. That is, when the object will be at C, when the object will be at focus, when the object will be in between the center of curvature and focus, when the object will be between the pole and focus. For these 1, 2, 3, 4 cases, you can draw the ray diagram and get the image and information, that is the position, size is less or large, real or virtual, this and that we can conclude by this ray diagram. Okay, so I hope you all understood this session. If you are something you have doubt, then do contact with me through the Urban Pro profile, and for the time being, see you in the next session. Okay, good day.